a pretty stupid greedy algorithm, and if I gave you this problem and asked you to come up with a greedy algorithm in 5 or 10 minutes, each of you would have come up with this type of an algorithm, right? What I'm trying to say is that it's the most obvious algorithm that everybody will think of, and to see that in fact this obvious algorithm still you can prove something related to optimality, that's reassuring, although the factor itself is not great. Okay, so let's see how to go ahead and try to understand why this is going to be within a factor of ln n. So So in the proof, what we are going to do is we are going to say, let K be the optimal solution. Okay, that is, let the optimal solution consist of K subsets. Okay, and then based on this, we will somehow establish the proof. Okay, so if K is the optimal cover, right, and let's say the greedy set cover algorithm that we have here, right? Let's say it has gone through t iterations, okay, and then after t iterations it has covered some number of elements, okay, and let's use nt, okay, let's use nt, right, to refer to the number of elements that are still not covered after t iterations of the loop. Okay, so this is where we are going to make use of the fact that there exists an optimal solution which has which has a size of k. Okay, so we know that, well, these uncovered empty elements have been covered by the k sets in the optimal cover, right? That's why the optimal solution is actually a cover, right? So therefore all of these elements must be in those sets. Okay, which means that each of these sets, k sets, must cover at least mt by k, right? Again, this is like a generalized pigeonhole principle, right? It just says, well, you have to get mt uncovered elements across k, right? Then there cannot be, there must be at least one set that contains at least mt by k, right? Because otherwise you can't make up that number, right? We are not saying that every set must contain at least mt by k uncovered elements. What we are saying is that there must be at least one, right? Because as you can see, on average, right, each set must contain mt by k uncovered elements, right? So the minimum cannot be less than the average, right? So therefore, there must be at least one set which has nt by k uncovered elements. Okay, and so because the greedy set cover algorithm is going to pick a set that maximizes the number of uncovered elements, right? Therefore, it's going to be able to pick at least this set and therefore reduce the number of uncovered elements by at least nt by k. So that is what we're going to say, and as such, if you write a recurrence, right, uncovered elements after t plus 1 steps equals, right, is going to be, so after, okay, let's write it down this way. So we said uncovered elements after t steps, we call that nt, right? And then what we said now is that in the t plus 1 step, the greedy algorithm will be able to find a set that covers at least nt by k new elements, which means that u of t plus 1 is going to be nt minus, or rather I should say, right? Because I have covered at least nt by k additional elements over what was covered after t steps. Okay, and this is nothing but nt times 1 minus 1 by k, which is, in other words, if you write it as a recurrence, then let's not a lot of room there. So in other words, what we are saying is that u of t plus 1 is less than or equal to u of t times, no, not ut, u of t times. Right? So I just replace nt by u of t so that you can see the recurrence more clearly. Okay? So now what you can do is once you have the recurrence, you can expand it out, and then you can see that ut plus 1 less than or equal to ut times, what is this? U of t times 1 minus 1 by k, which in turn is less than u of t minus 1 times 1 minus 1 by k whole square, and so on. And at the end you will say u0 of 1 minus 1 by k whole power t. Correct? So all we have done is we have used this recurrence, and again what we are saying is that each time I should be able to find at least a certain number of uncovered elements. The greedy algorithm should be able to find at least a certain number of uncovered elements, and we use that to form this recurrence, and then we expand out the recurrence, and then we get this solution. We of course know u0 is n, right? After 0 iterations, nothing is covered, so this is n. So what we are saying is n into 1 minus 1 by k whole power t, right? Which we know our trusty expansion of e to the power something, right? So if we supply that, we know that this 1 minus 1 by k power something, right, is of the form of e to the power something. So, and this is the relation. So we have 1 minus 1 by k to the power t, right, is e to the power minus t by k, right? Because that's this is equal to n times 1 minus 1 by k power k whole power n, right? And we know that 1 minus 1 by k whole power k is nothing but e to the power minus k, right? So this is why you get e to the power minus t by k, where the t is right outside here, right? So I'm sorry, this is t, right? So t to the power. So you get the solution, and again we know, again we are familiar with this type of equation. We have looked at it in randomized algorithms several times. So we know that if you do this when you set t equals k ln n, right? So you set t equal to k ln n, then the k will cancel out this k, so you'll have e power ln n, right? And so e power ln n, or rather e power minus ln n, right, is going to be 1 by n, which means that this whole thing is going to be less than 1. So after that many iterations, you will end up with less than 1 uncovered element, which means that you have a full cover, right? Because obviously you can't have less than 1 uncovered element, right? It's a strict less than so far. And so what we know is that after k ln n steps, right, we would have completed the cover, right? And that tells you that obviously we are adding 1 element per step. So if we are going through k ln n steps, then the size of the set cover will be k ln n, right? So we have computed a set cover that's of size k ln n, whereas the optimal size is k, right? That's what we started out with. Thus, we have an approximation algorithm which is within a factor of ln n. Okay, so that is your greedy set cover algorithm. So now, let's look at a problem that sounds quite similar, right? Vertex cover, right? Because again, we are trying to pick vertices that cover all edges, right? And we can in fact, the way I describe it, you can already intuitively see that it is like a covering problem, right? But here is a formal definition. So the set of subsets we are looking for is like this, right? Each set consists of edges that are coming out of a particular vertex, right? So, and then there is one such set for each vertex, right? So there is, so this collection of sets contains one set for each vertex, and for that vertex, it lists all the edges incident on that vertex. Okay, so now with this formulation of set cover, the set cover will actually be a vertex cover, right? Except that, of course, as I said, ln n is, not really a great number. Who wants, a set cover that's within a factor of ln n? So, question is there something better we can do? And it turns out that we can actually do something much better, and the algorithm is almost trivial, right? So, here is the algorithm, right? Or here is the reasoning. So you take any edge, right? So in a set cover, this edge must be covered, right? And that means either one of the two vertices that this edge connects must be in the optimal set cover, correct? So the problem is, of course, if you have a non-deterministic algorithm, then it can be given these edges one by one, and it can, guess the, optimal choice and pick either u or v, right? And now what we try to do is we try to say, okay, suppose we don't have the oracle, right? And why not do something very simple, which is to pick both, right? Now we know that the oracle is picking at least one of them, and whenever the oracle is picking one, I'm picking two, right? Which means, very trivially, I'm able to establish that the solution that I obtained this way is within a factor of 2 of optimal, right? It's a very, very simple way to do this. And so that's your approximate vertex cover algorithm. And of course, you start by initializing the cover to be empty set, and then you pick any edge, and then you add both sides to the cover, right? And now what you want to do is you want to say, okay, now I have added these two vertices. That means I obviously have covered every vertex, every edge that's incident on these vertices, right? These vertices u and v. So what I'm going to do is I'm going to say, okay, I obviously don't have to pick any of those vertices, right? Any of those edges anymore. Like I already covered them. So I'm going to sort of simplify my problem by deleting both the vertices from the graph. Okay? And when I delete both vertices, that means all the edges associated with them will also be deleted. Right? So what I'm doing is I'm just picking a random edge, including both sides as part of a cover, right? And then I'm just deleting all the edges on those two vertices, right? So now, because I already covered them, right? I don't have to consider any of those vertices again. It's kind of silly because I already have covered them. I know that I have covered them. So I just do that, and then I'm going to end up with a solution which is within a factor of 2, and obviously this is a polynomial algorithm, right? So because each time I spend at most this takes linear amount of time at most, and this step, modifying the graph, again takes at most linear time in the size of the graph, which means that this whole algorithm could be at most quadratic, right? Because the number of iterations, each time you go through the loop, you are at least deleting 2 vertices, right? So you can't do the number of iterations cannot be more than linear, and the cost of each iteration is also can't be more than linear, which means that it's a polynomial time algorithm which achieves a factor of 2 within vertex cover. Right? So it seems great, except that you probably are not too happy, just because it's so easy to do, right? It already tells you that this is probably not a great solution. Okay, so but again, whether the approximation factor is satisfactory or not depends on the context, and there certainly can be contexts where a factor of 2 is perfectly acceptable, right? And then there could be contexts where it's not acceptable. So this is the next problem we are going to talk about, K-cluster, which is also called facility location, right? So I'm sure you no longer remember that from one of the earlier slides, but the term facility location is also used to refer to this. So the idea here is that you have a bunch of, think of a problem like you have a bunch of, towns, and you need to locate, say, telephone exchanges to connect to them, or power stations to supply power to them, right? So the idea is that you want to consolidate these facilities, right? So that you don't want to have one of them in each, far-flung village. So the question is, where can you put them so that the amount of wiring that you have to have and so on is not too much, right? Between the centralized facility and the individual villages. So the abstract problem is you have a collection of points, right, x1 to xn, and there are distances between these points, right? Again, we think of them as in 2 dimensions, right? So we have distances, and then you want to partition this into k clusters in such a way that the distance between the in such a way that minimizes the maximum cluster diameter, right? So what does that mean? So we have points like this. Then you might choose, let's say, this as a cluster center, that as another cluster center, this one, and this one, okay? And then all of these other entities are going to be connected to the cluster center, right? And in some ways, the amount of wiring that you need is proportional to sort of the diameter, right? The diameter is the distance between the 2 farthest points within the same cluster, okay? So essentially, if you so this is the cluster diameter, and here again, if you draw a circle, again, the diameter basically says what are the 2 points that are farthest from each other, right? And that gives you an idea of how much wiring you use, right? So what we are trying to do is we are trying to figure out, given those points, how do you identify cluster centers? Okay, and again, this is an NP-complete problem if you want the optimal solution, and we are interested in approximating it and coming up with an approximate solution that actually has is within some factor. And the way we are going to do this is by an iterative approach. The first step is going to pick an arbitrary location. It doesn't care. Okay? It picks an arbitrary location as the first cluster center. Okay? And then what it is going to do is, at the next step, it's going to pick, so mu1. Mu1 is chosen arbitrarily. Then mu2 is chosen to be the element that is the location that is farthest from mu1. Right? The idea is that you want to spread out your center so that you can maximize the likelihood of forming these clusters. Right? So let's say your first cluster that you chose was here. Right? Then you might say, okay, I'm going to choose the farthest point from here, which in this case appears to be this one, right? Maybe. So the idea is that you pick the farthest one, and then now you have these two things to cover. Now, what is going to be uncovered, right? What's the points? What we are doing is now. So once we have these, right? So these points probably have some center that's close by, right? So which are the points that don't have a center close by? Those are the points that are as far away from these two chosen centers, right? Because everything that's close by, well, you already have a center that's close by. You don't have a center close by if for points which are right now far away from every center that you have chosen, right? That is the rationale for this step, right? So the new center that you're going to choose at every step is going to be the point that's farthest from centers that are already chosen. Okay, so this way you reduce, you increase the likelihood of finding centers close to every point in this collection. Okay, and you keep doing this, and you have been given a budget of k, and so you do this k times, and then you're done. Okay, and now the question is, how well have I done, right? So if I now look at the cluster diameter for this algorithm, right? This is obviously a polynomial algorithm, right? So for this polynomial algorithm, it comes up with a cluster diameter of something. How does that compare with the octet? Okay, so again, that's what we will try to discuss here. So now let's say that we have finished with this algorithm, right? So we have chosen, again, our budget was k. That means we chose centers mu1 through mu k. Okay? Now consider the point x among all of the points that we have, which is farthest from any of these centers, right? So it's in a sense the worst case example for us, right? And then what we can say is that the cluster diameters at most 2r, right? Because obviously the worst case point is at most a distance r from its center, right? And you can see here that the distance from the center is like the radius of the circle. So if we want diameter, then we want 2 times the radius, right? So what we are saying very simply is, let's take the worst case point, right? The point that's farthest from all the centers, right? And what is the distance? That's r. Then the diameter that we have computed is simply 2r. Okay? So now we want to compare this 2r with what an optimal solution might achieve. Okay? So how do we do that? So what we are going to say here is this, right? So we're going to say that consider the set of points x mu1 to mu k. Okay? What we are going to show is that now so what we are going to say is that the distance between any of these 2 points, right, is at least r. Okay, so how do we show that? Well, first of all, let's say we ran this algorithm for one more step, for k plus 1 step, correct? So if we did that, then x would have been the point that it chose for the k plus 1 step. So we can actually call x as mu k plus 1, right? And then the way we are choosing this mu1 through mu k, right, clearly the distances should be dropping, right? Each time we are choosing the point that's farthest from the previous points, right? So the next time you choose a point, that's not going to be as far, right? So the distances, the maximum distance that you're picking, right, is going to be falling all the time, right? So this mu k plus 1, right, the distance from other points should be less than or equal to the distance between mu k and the other points and so on, right? As a result, all of these points, so as a result, if you pick any two, right, mu1, mu2, or mu5, mu7, those have to be at a distance greater than mu k plus 1, because all of those distances are greater than the distances of the subsequent points that you pick. Okay? So which means that you have at least k plus 1 points here, right? Mu1 through mu k plus 1. At least k plus 1 points that are pairwise at a distance of r or more. Okay? And that tells you that if you use some circles to cover this, right, you have pairwise at least a distance of r, right? And there are k plus 1 such points, right? So you cannot do better than a distance of r between clusters that contain these points. Okay? So you again, we have so if you have an optimal k cluster, right? Again, what we are trying to say here is that there are k plus 1 points that are pairwise at a distance of r or more, right? And then if you try to draw k circles around k plus 1 points, right? Then at least one of these circles must include two of these points, right? So you are trying to cover the space with k circles, right? And you have k plus 1 points here. So this means that there must be at least one circle that must include two of these points, right? And since any 2 points are at least distance r, this circle that includes 2 points must have a diameter of at least r, okay? Which tells you that the optimal solution, again, must have diameter at least r, right? Whereas the solution that we compute has a diameter of at most 2r, right? So as a result, we have an approximate solution that is within a factor of 2. Okay, so once again, we have a factor of 2 approximate solution. And again, in this case, it seems, at least intuitively looking at the problem, it seems okay. It's the factor of 2 is not such a bad number. So let's finish up. We have a couple more, and these are actually the TSP is actually extremely simple. So we want to do Euclidean TSP, and we want to find an approximate algorithm for Euclidean TSP. And our starting point, we've already done this before, right? So where we are trying to establish bounds on the cost of TSP, we said that the minimal spanning tree cost is a lower bound, right? So we know that the optimal solution cannot be less expensive than the MST. Okay. So what we're going to do is we're going to start with the MST. Okay. So let's say here's an example, right? So you are trying to find a tour through all these cities, right? That is of minimum cost. So what you do is you first construct the minimum spanning tree. Okay. And then what you do is you construct a way to visit all of them and come back to the original city, right? And this is not a tour yet, right? Because you go forward and backward. So what we do is you're going through this from one city to the next, and then you come back from Wichita to Tulsa, then go to Little Rock and all these places, right? And then when you're done, you're simply going to retrace your path back to El Paso, right? So if you do this, then you have a path that visits all vertices, and its cost is less than twice the cost of the minimum spanning tree. Right? So that's clear. Now, how do you convert it into a tour? Right? Because right now you're going back and forth on the same edge, and the definition of a tour is one where you don't traverse any edge more than once. And the way you do that is quite simple. What you do is, so let's say you go this way, and then you go there, right? Now, instead of coming back on the next edge here, instead you can short circuit to the next unvisited city. Okay, so now what can you say? What you can say is that if I came back through the original path, then I would have come from Wichita to Tulsa and Tulsa to Little Rock. Okay, but again, I'm working in the Euclidean plane, so instead of going through Tulsa to Little Rock, if I went straight from Wichita to Little Rock, then the cost of that path should be smaller. So what I'm doing is I'm taking this path that traverses the MST edges at most twice, right? That's my starting point. And then I'm converting that into a tour such that the cost of the tour is less than this MST traversal, right? So I have a solution which, right? So what we do here is so for instance, instead of going this way and that way, you can go straight to over there and then come back. Okay, so the basic idea is simply that instead of going back and forth on the visited edges, if an edge is already visited, you just short circuit to the next unvisited vertex. And when you do that, what you're going to do is you are basically able to take advantage of the triangle law inequality and show that this short circuiting will only reduce the cost. Okay, and as a result, you will end up with a solution whose cost is less than or equal to 2 times the cost of MST. And we know the MST is already a lower bound on the optimal solution, which means that this approximate algorithm for TSP is achieving at most a factor of 2. Is at most a factor of 2 worse than the optimal solution. Okay? So that's the TSP. So finally, let's look at this knapsack. And this is the one example where we have this polynomial time approximation scheme. Right? So where we have a solution that is within epsilon from the optimal, and we can control this epsilon, and we can reduce epsilon, and that will mean that we have to spend time that increases in a way that's inversely proportional to epsilon. So here's the knapsack problem. It's an algorithm that we have looked at, but there is a slight change here. So in the original knapsack, what we did was we computed partial solutions for different weights, and then we pick out of these partial solution the one that gives you maximum value. Okay, so in the original knapsack we looked at, the second so this subscript, if you recall, is the item number, right? So k of j means you have considered including all items from 1 to j, right? You haven't considered including any item above j. And then the second subscript was based on the weight in the original algorithm, right? So, and then we pick the maximum value, right? Here what we're going to do is we're going to do it a little bit differently. We're going to compute for different values and then pick the maximum value with which is less than the weight bound. Okay, so we're just going to do the computation in a different order, right? For different values, what is the minimum weight that we can achieve? Okay, and that's what we are doing here. So we are saying that to include, if you want to include the jth item, then your solution will be the best you can obtain with j minus 1 item, right? Or you include the jth item, in which case your weight increases by w of j, right? And then you are going to limit yourself to a partial solution which has j minus 1 elements and the value of b minus bj. So what we are trying to say is that for a value of b and up to j, what is the minimum weight? And that's why this is a minimum, right? So instead of saying for the weight, what is the maximum value, right? That's the original formulation. So you can change these things around and it won't make a lot of difference, but it is this formulation that we can actually apply a polynomial time approximation. And recall that the knapsack has a complexity of order of nV, where n is the number of items and v is the sum of values. Again, previously this v was a w because we were populating this two-dimensional array where the second subscript was on w. Now the second subscript is on v, so it's going to be order of nV times. So now the fully polynomial time approximation scheme, what we are going to do is basically we are going to say, look, we don't have to, again, the reason why order of nV is bad is because v could be arbitrarily large, right? And when viewed as a problem size is only of log n size, log v size, right? So because you need only log v bits to represent v. So the problem size is only log v, but then we need time that's v, right? So what we need to do is we need to decrease the range of v. Okay, so that's the way we are going to get to a faster algorithm, right? So again, we are not really going to change this algorithm. We are going to continue to use this algorithm, right? And what we are going to do is we are going to say somehow remap the values into a smaller range such that this v will become much smaller, and in fact small enough that it will now become polynomial time algorithm. And that's exactly what we're trying to do. And how do we do that? What we are doing is we're saying, okay, I want to accept an error of epsilon. Okay, so what I'm going to do is I'm going to use this multiplication trick here, right? And what that is doing is it's in a sense scaling the values, or you can think of it as normalizing the values, right? So your denominator is the maximum value among all of the items, right? So essentially you are normalizing the value. Vi by Vj gives you sort of, how much is the value of one item as a fraction of the value of the most valuable item, right? So that will give you, obviously if you just take that will become, and then you take the integer value, it will all be 0 except for that item which has the maximum value, right? Because Vi will always be less than or equal to Vj, right? Because Vj is the maximum here. So that's not what we want, so we need to, multiply it by some factor so that, you will have some numbers that are greater than 1. And the factor we are going to use is n by epsilon, okay? And if you use a factor n by epsilon, then you can show that, in fact, the error that you get is going to be again, you can do the calculation. What you will find out is that the original values, if you add them up, and the scale values, if you add them up, the difference would be at most epsilon apart. Okay? And so that's what you want in terms of the approximate algorithm. You want to make sure that the value that you achieve is within 1 plus epsilon times the optimal value, right? And so if you apply this, then you're guaranteed that your solution is going to be within 1 plus epsilon. And then now let's just do the complexity, right? So we have again, the complexity has to change because all we did was after rescaling, we are simply reusing the original knapsack algorithm as it is. So its complexity applies. So it's going to be O of n v prime, because v prime is, because we have rescaled the values, so it's going to be v prime. We just have to substitute for v prime and see what happens, right? So what is v prime? We want to obtain an upper bound on v prime. And you see that upper bound on v prime, right, is going to be n times vj, right, because vj is the maximum. So upper bound is going to be I'm sorry. So take the maximum among vi primes and multiply that by n, right? That's going to be an upper bound on v prime, correct? So instead of adding up the costs of v1i, v1 prime plus v2 prime plus v3 prime and so on, we get a quick upper bound by taking the maximum among vi primes and multiplying it by n, right? So that's what we are doing here. So v prime has been replaced by n times maximum among vi prime, and then we are substituting for vi prime. Okay, so what is vi prime? So you can see that the maximum that this factor is going to be is 1, right? Because the denominator is the maximum among vj's, so the numerator could at most be equal to the denominator. So this whole thing is going to be at most 1, which means that this whole quantity is going to be at most n by epsilon, right? So that's why we can replace this max vi prime by n by epsilon, and then we do the arithmetic, we get a complexity of order of n cubed by epsilon, right? So it's no longer exponential, it's a polynomial where the approximation factor epsilon appears in the denominator. So again, as you want a solution that's closer to the right answer, you end up with something, you end up having to spend more time, right? But again, you can see that this is not bad, because let's say if you want epsilon to be 1%, then you have to spend 100 times n cubed, which is still polynomial as compared to the original exponential time algorithm. Okay? So that's, gives you a flavor of approximation algorithms, and I guess that brings us to the end of this course. So the final is on Wednesday, right? So again, we are going to have a final exam which combines elements of the first and second midterms, right? So that's the whole idea of why the two midterms were like this. So you would have probably an hour, half an hour to 45 minutes of time on multiple choice or short answer questions, and the rest of the time on solving problems similar to your midterm 2.